This is a tiny piece of metal, just 3 millimeters across. Zooming in reveals its atomic structure, 1,000 times magnification, 100,000 times, and finally, 50 million times. Each visible blob is an individual atom. This feat, recently witnessed at the University of Sydney, was considered impossible just 30 years ago. The labs housing this incredible technology are among the most shielded and expensive on the campus, perhaps even in all of Sydney. Why is visualizing atoms so challenging? Visible light, with wavelengths between 380 and 750 nanometers, cannot resolve objects as small as atoms, which measure only about 0.1 nanometers. When the wavelength of light is significantly larger than the object being observed, the light diffracts, bending around the object instead of reflecting it, rendering it invisible. To see atoms, a much smaller wavelength is required. Electrons, not light, are the key. In 1924, Louis de Broglie theorized that everything, including matter, possesses wave-like properties. Atoms, molecules, and even humans have wavelengths, defined by Planck's constant divided by momentum, mass times velocity. The microscope used in this visualization accelerates electrons at 300 kilovolts, making them relativistic particles moving at approximately 80% the speed of light. This translates to a wavelength of 2 to 3 picometers, over 100,000 times smaller than visible light, theoretically offering 100,000 times greater resolution. Following de Broglie's discovery, German scientists began developing a microscope using these high-speed electrons. However, electrons cannot be focused with glass lenses. Hans Busch proposed using electromagnetic lenses, publishing his theory in 1926, though he never built one. Ernst Ruska, a PhD student, seized upon Busch's paper. He created the first electromagnetic lens by coiling wire around iron, leaving a gap in the center. Passing current through the coil generated a donut-shaped magnetic field, focusing the electron beam. Ruska's prototype used a tungsten filament to generate electrons, which were then accelerated toward the electromagnetic lens. The magnetic field exerted a force, Lorentz force, on the electrons, causing them to spiral inwards and converge at the center of the lens, focusing the beam. By 1931, Ruska and Max Knoll had built the first working electron microscope. This primitive device, constructed from brass, successfully focused an electron beam onto a thin sample, around 100 nanometers thick. The resulting electron imprint was magnified by a second electromagnetic lens onto a fluorescent detector, creating the final image, a transmission electron microscope, TEM. Early versions of the TEM had limited magnification, barely surpassing optical microscopes. Ruska persisted, adding more lenses to achieve higher magnifications. By the mid-1930s, the TEM could magnify over 10,000 times, revealing details of insects, bacteria, and viruses far beyond the capabilities of optical microscopes. Just as the TEM was gaining momentum, Otto Scherzer published a paper identifying an insurmountable flaw in electromagnetic lenses: spherical aberration. This distortion arises because the magnetic field does not scale linearly, over-deflecting electrons at the edges of the lens. This results in a blurred focus, worsening with increased magnification. Spherical aberration affects all spherical lenses, but it can be minimized by adding a diverging lens. However, this is impossible with magnetic lenses, as they always converge the electron beam. This limitation, proven by Scherzer, stalled TEM development. Despite this setback, other techniques emerged. The field ion microscope, developed in 1955, imaged atoms by projecting ionized gas atoms onto a charged needle tip. While groundbreaking, this method had limitations. Work on the TEM continued. Albert Crew replaced the random tungsten filament with a brighter, more directed electron source, pulled from a sharpened tungsten tip using a strong electric field. He paired this with a cathode ray tube-inspired scanning system, creating smaller electron imprints and mapping the sample bit by bit. In 1970, Crew achieved the first images of individual atoms using an electron microscope. Despite these advancements, spherical aberration remained a fundamental limitation. Even Crew eventually conceded defeat in overcoming it. Other probe microscopes, which felt atoms rather than seeing them, emerged, but they lacked the direct visualization of the TEM. Scherzer's theorem, however, only applied to radially symmetric lenses. 3 scientists, Knut Urban, Max Heider, and Harold Rose, proposed breaking this symmetry to correct spherical aberration. Their radical idea involved distorting the image with non-symmetric lenses, hoping to find a diverging component that could counteract the aberration. They used hexapole, octapole, and decapole magnets to distort and then unbend the electron beam. This complex process aimed to introduce a counteracting spherical aberration. Initially dismissed as impractical, their research struggled for funding. Facing imminent funding withdrawal in 1997, they finally achieved success. After countless failures, their latest lens, incorporating the corrective magnets, stabilized, producing clear images of atoms. This breakthrough reduced the TEM's resolution to 0.13 nanometers, dramatically improving image quality. Urban's presentation of these results at a microscopy conference initially went unnoticed. However, word spread, and a large crowd gathered to witness the stunningly sharp images. Shortly after, Andrei Krivonek independently achieved the same correction for Crew's scanning TEM. In 2020, Urban, Rose, Heider, and Krivonek received the Kavli Prize in Nanoscience for their groundbreaking achievement. Aberration correction revolutionized electron microscopy. It enables the visualization and analysis of atomic structures, crucial for fields like materials science, materials engineering, and chemical engineering. Without this ability, researchers would only have half the information needed to understand the relationship between a material's properties and its structure. It was a true game changer.